Welcome back, guys, to Lecture 2 of Section 21.5. We'll be finishing up the chapter and talking about three more functional groups, carboxylic acids, esters, and amides this time. So we'll first start with our talk of carboxylic acids. And before I go to the next slide, I'll just remind you, last time we talked about carbonyl groups, as in this carbon connected to an oxygen with a double bond. This is an aldehyde. And we have a version of a ketone where this could be the same group as this or a different one. It could be R prime. Instead, carboxylic acids look like this. So we've seen these before. When we used acetic acid many times in our discussion of weak acid equilibria, and instead of an alcohol straight up like this propanol, this is a weak acid and this is not. This can do acid-base chemistry very easily. This is quite difficult to deprotonate. So that's our first discussion. And where do we get those? Well, we can start with alcohols. So if you take an alcohol and oxidize it, we can get our actual aldehydes and ketones. So that's how we actually get the aldehydes and ketones in the first place. So when you do that one more time, you can actually get a carboxylic acid. And before we draw structures, things like that, let's try to remember oxidation. Before we define oxidation as loss of electrons. In organic chemistry, the way we use that word, it's a little bit different. What we are saying is, think oxidation, increase the amount of CO bonds. So going from an alcohol, OH, to a this is going to be better with carbons. Let's say I have an alcohol here, and this is an R group, and this is an R group. If I oxidize this, I want another bond to alcohol, or to oxygen rather. So I make a carbonyl group. That would be oxidation. You're increasing the amount of bonds to oxidation. So in the world of organic chemistry, that's what we mean by that. Reduction is the opposite. You're decreasing the number of CO bonds. So this is an error right here. Oh, decreasing CH bonds. No, that's correct. So reduction increases the number of CH bonds or decreases the number of CO bonds. So we can use both of those to define oxidation and reduction in organic chemistry. So again, oxidation, you are increasing the number of CO bonds or you're decreasing the number of CH bonds. Reduction means we're getting more CH bonds or less CO bonds. So when alcohol is oxidized to an aldehyde or ketone, we're actually forming one more of these and eliminating a CH bond, right? Because we had a CH bond here, and now we eliminated that CH bond in that oxidation process. So this will help us actually look at that in the next slide over. We have primary alcohols, secondary alcohols, and tertiary alcohols. I'm just going to go to the next slide and actually look at these. This will help us visualize this better. So if we start here at a primary alcohol. So a primary alcohol means we have one R group bound to the carbon, and these are both H's. So that's a primary, just one. Notice the secondary alcohol, we have two R groups, and a tertiary, three R groups. There are no CH bonds there. So there's no CH bond to oxidize, actually. So what we can do is get three different products here. If we start with the primary, we can go from a primary alcohol to an aldehyde. Notice our CH bond, we have one less CH bond, and we have one more CO bond. Just so happens that instead of a single double bond, we have a C double bond O. And notice we don't keep this H. This goes from an alcohol group to a carbonyl species. So primary alcohols are oxidized to an aldehyde. Secondary alcohols, if there's two R groups on here already, they can get one more bond to oxygen, but that's it. They have to stop here. You can't oxidize that anymore. You've got your ketone. Aldehydes, though, notice I can oxidize that one more time to get all the way to another bond, a carboxylic acid. So I could go all the way with an aldehyde there, but I can't with a ketone. You can't oxidize this anymore. And notice down here, our tertiary alcohol, this will not be oxidized. If you tried to draw this with a carbonyl, well, there's no CH bond to get rid of. So you'd have to get rid of one of these R groups, and that's very hard to do. And this is 5 bonds. No, everything about that is bad. So you can oxidize a primary alcohol to an aldehyde, and you can oxidize a secondary alcohol to a ketone. You can also do the reverse. If I reduce this, I get back to the primary alcohol. Now if I reduce this, I get back to the secondary alcohol. So that's how we form these aldehydes and ketones from alcohol species. Now, the compounds used, well, there's quite a bit that can do that. We're not really going to dig into that in general chemistry. When you take organic chemistry, you'll learn of a lot of different compounds that can actually do these oxidation processes. However, if you're careful, if you take a primary alcohol, using the right compound, you can just oxidize it to an aldehyde. However, if you use a stronger compound, a stronger oxidizing agent, it will continue on and you're going to oxidize it all the way to a carboxylic acid. Let me draw these out for you here. This is 1, 2, 3, carbon, 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 OH. So this will go to the aldehyde. That's how I would draw that. And then carbon, carbon, all the way to the carboxylic acid. So you can take one, go all the way to the carboxylic acid, starting from a primary alcohol. So the structure, if you look at this, you need to remember there are lone pairs there on our alcohol group. So when this gets deprotonated, oops, I just turned on a separate thing, stop that. When this gets deprotonated, so a base comes along, grabs this, these electrons go here. And we have this minus charge. But in reality, remember we learned this is in resonance with this bond here. Or we should put an R group here or something. So this becomes R, C, O, O, minus. It's that resonance, that stabilization, that makes this compound pretty willing to give up this H minus, this H plus. It's somewhat stabilized like this, so it's okay with being deprotonated. So these act as weak bases. And when we're talking about the functional group itself, we refer to this whole thing, the COOH group, as the carboxylic acid functional group. We kind of lose the alcohol. We don't really think of this as an alcohol anymore. So this we think as a carboxylic acid functional group. And you'll see it written condensed as RCOOH. That equals the same thing as this structure here. So me, as I'm always curious where we find these things. So they're weak acids, and we find them a lot in fruits. So kind of interesting where they drew these, but if you look, let's see if we can't turn this into a structure that is a little bit more condensed. Nah, it's going to be tough to draw it here. You can see this. This is a C, this is an OH over here. So in this structure, we have 1, 2, 3 carboxylic acids in citric acid. So a lot of lemons and oranges, limes, the very acidic fruit, we find this one. So these 3 carboxylic acid groups are 3 ways that make this acidic. Malic acid is also very tart, but not as tart as citric acid. So it's in different fruits. You see that in bananas, watermelon, grapes, things like that. You've got a carboxylic acid group here, and you've got a carboxylic acid group on this side. Tartaric acid, you'll find those in other fruits, but also we have avocado and tamarind. And there we've got 1 and 2 as well with some alcohol groups. So some other organic acids they show down here. Benzoic acid, which is cool because we just talked about benzaldehyde in the last section. So benzaldehyde looks like this. So you can go from this to benzoic acid if you oxidize this. If I oxidize that and increase the number of bonds, I can get to benzoic acid. So just some interesting compounds that we find. We see lots and lots and lots of these carboxylic acid structures out there in the world. Okay, so how do we name these? Systematic name. We have something like methanoic acid or pentanoic. Well, if it's a pentane, we change the A and E to, oh, I just wrote petane. Let's retry that. Pent to pent, so you have that oic. Pentanoic instead of pentane. So we've got that butane, butanoic, methane, methanoic, propanoic, etc. So this we see, remember this is always going to have a chain that ends, just like an aldehyde. So you don't need to know, you don't need to tell that this is one. It's not at the one position, one pentanoic. It's always going to be at the one position, regardless of how long the chain is. So we don't actually have to use a number to tell you where the carbonyl is. Pretty similar to how we name aldehydes. So don't need the one. So this is the smallest one, methanoic acid, similar to acetic acid. Remember, acetic acid is not the correct systematic name. Oops. Acetic acid is this. What would the actual systematic name for acetic acid be? One, two. So we need our ethane, and we just say acid, ethanoic acid. So acetic acid is actually called that. So let's do a couple of practice. We're going to go from names to actual structural formulas here. So give yourself a second and pause to draw these. And you can do it in a structural formula or a skeletal structure with lines and dashes if you'd like. Okay. A, hept. Okay, hept is what, 7? So we need to make sure we've got 7 carbons. So a condensed structural formula, you could do CH3, CH2. Oh boy. 1, 2, 3, 4, 5, 6. And finally, C double bond O, OH. So that's one way you could draw that one for heptanoic acid. You could do the skeletal structure instead, though, and just do start here for 1, 2, 3, 4, 5, 6, 7. Notice I ended going down arbitrarily. So that means I need to draw this downward. And then double check. 1, 2, 3, 4, 5, 6, 7. Yeah, so there'll be a structural formula. If you happen to start up, which I rarely do, I usually start going for there. You could do 1, 2, 3, 4, 5, 6, 7. Equivalent structures. 1, 2, 3, 4, 5, 6, 7. Yep. So there's that one. Okay, what do we have here? So octanoic acid. So we have to have 8 carbons is our longest chain here. Oic acid, so that tells us, yes, it's carboxylic acid. And this is a 5-methyl. So at the 5 position, we have a methyl substituent. So let's go ahead and draw out our chain first. And I'm going to do the skeletal structure first. Let's try that. So if I do the 1, 2, 3, 4, 5, 6, 7, 8. Remember, we start counting from that position to get our substituents right. That's the 1 position. We don't count the 1 over here. I just started with the 1 in my head because I was trying to count these out. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I got my 8. Now I just need to count 1, 2, 3, 4, 5. That'll be my methyl group. That would be the condensed skeletal structure formula for this. Let's go to the next slide to double check to make sure ours match up. Yeah, so this looks pretty good. And oops. And this is how you would draw that out with just more of the condensed version. And notice they're using bonds too here because honestly, this style is just kind of clunky. You don't see that very often. If you're going to do all this long chain, you're pretty much always going to see this way. This, they're making some bonds just to kind of break this up to show this is the 5 position. But even this is not too often shown that way either. But that's the way that we practice in this class. Okay, so this is just mentioning kind of what I mentioned before, that these are weak acids. So these are not ionizable. It's the one right here. So when we draw these out in these type of formulas, we'll see the COOH group explicitly drawn like that to show that this is a carboxylic acid group. So this is acetic acid / ethanoic acid, and this is as well. It shows the connection point between these two. So that is our weak acid style. And we saw this so much in the last chapters. CH3COOH plus water. This is the one that's going to get donated to water. And that's why we'll write that deprotonated there with our H3O plus over there. Okay, so that's carboxylic acids. Now, what if we take one of these and react it with an alcohol? Notice that is an R. That's an R prime. So an ester is taking, I'm going to also highlight this H and this OH. So what we're doing here, this is a condensation reaction. We are condensing. Condensation means, think of water from gas going to water vapor, or sorry, vapor going to liquid. Condensing. It's kind of where they got that from. So we're condensing these two structures into an ester and water, and we're getting water as a byproduct. So this R group is now connected to that carbonyl. Oh, I'm sorry. What am I doing? Get out of here. The R group is now OR. And actually what happens is this entire, and we're not going to get into this now, but this is what attaches to the carbonyl. It's this O and R that goes to the carbonyl. But we're not going to learn about the mechanisms in general chemistry. So you just need to remember that an acid and an alcohol reacting together, you're going to get this new compound called an ester, and water is a byproduct. So that's why I highlighted these out. This will help you remember what the product looks like. Think, here's my water piece, and then this R group's going to be here on my new structure, this new R prime. So esters are found in all types of flavorings and smells and fruits and all kinds of places. So if you do this condensation reaction in lab, if you change the length of this group and this group, you can imagine what kind of combinations of esters you could get. Maybe this is 3 carbons long and this is 7 carbon chain. This is 2 and 2, 5 and 6. One of the really fun organic chemistry labs is to create your own esters. In lab, you can use a catalyst to do this, basic or acidic, and you get these really flavorful compounds. We actually did this in general chemistry when we made the wintergreen ester. So I went online, as I do, because I love looking at this stuff up, to see where I could find some of these. So this is a really cool table showing from, okay, this is from the alcohol. So as in, if we had 1 carbon alcohol, as in CH3OH, so this is methanol, plus we wanted to do butanoate. What would butanoate look like? Butanoate would be our carboxylic. Oh, I'm sorry, that's the ester that we get. methylbutanoate. We haven't talked about how to name these. What that's saying though is we're getting a 4-carbon long. Actually, I'm trying to figure out how this works. Methylbutanoate. Okay, never mind. Here's our methyl group. 1, 2, 3. You know what? Before I go through this, we need to learn. I want to teach you guys how to name these. So let's come back to this chart. How about that? We'll come back to this chart in just a second. So let's learn actually how we put these together. So naming these, we'll come back to that chart. So the name of an ester is a combination of the name of the hydrocarbon group of the alcohol plus the parent acid. We change that to OH. For example, methanol, here's our ROH, and ethanoic acid, here's our, if you go back to our COR, there's our carboxylic acid. We would call the resulting ester methyl ethanoate. And yeah, many simple esters have pleasant odors. And that's what I was getting at with that picture over there. So let's practice naming something first. So it says use condensed structural formulas to write an equation for the reaction of 1-propanol with acetic acid. So first of all, let's think about what this is asking us. 1-propanol and acetic acid. So what is 1-propanol? Prop, we need a 3-carbon chain. Anol means we have an alcohol, and it means at the 1 position, we have an OH group. And all those lines are going to be our hydrogens. So we've got CH3, CH2, CH2, OH, for example. Or if you want to do the skeletal structure, 1, 2, 3, it's just good practice. 1, 2, 3. 1, 2, 3. Even though I don't think the book even has you do these, I still like to show these to you. OH. So use the condensed, so it wants us to use the condensed, so it really wants us to use this one right here. And then we're adding acetic acid. Okay, remember acetic acid is not the systematic name, but this is the 2-carbon, think eth, 2-carbon. So it'd be plus OH. Okay, so remember what happens when you add an alcohol to a carboxylic acid. You're going to get this chain coming off of this alcohol now. So that's going to be our product. It's this R group that's attaching to the alcohol. So we're going to get H3CCO CH2 CH2 CH3. So there we go. So how do we name this beast? When you're looking at esters, think of, let's go back to the naming rules for just a second. It is the combination of the name of the hydrocarbon group of the alcohol plus the name of the parent acid. So the parent acid is where you get this ethanoate from. So if this was ethanoic acid, we use ethanoate. So remember, this was ethanoic acid. That's why I don't know why they said acetic acid. They should have said with ethanoic acid. So this is going to be some sort of ethanoate. And then what's on the O? What came from that? That is a 1, 2, 3, a propyl group. So we would call this propyl ethanoate. Propyl ethanoate. So now let's look back to this. These are all the different esters with the different smells. So actually, let's look this up. What would propyl ethanoate smell like according to this chart? This compound right here. So we can find that. So we would go to propyl, 3 carbons. That would mean we have a 1, 2, 3. I'm going to draw that differently. 1, 2, 3. There's our propyl group, right? I'm drawing. Oh, I'm sorry. Yeah, propyl. I got this wrong, I believe. Sorry, the ethanoate is here, and the propyl is over here. So let me redraw this. Bear with me here. That's why that confused me. Propyl ethanoate. That's going to be pear. So propyl ethanoate actually smells like pears. So again, if I wanted to try to draw that from this propyl ethanoate, the propyl group is going to be what's coming off the O, CH2, CH2, CH3, and the ethanoate is what's coming off over here. Let's practice drawing another one from this graph. So let's try to draw hexyl pentanoate. Hexyl pentanoate, which, by the way, looks like brandy, something you might find in brandy. So you find these things everywhere. You'll see mint leaves, nuts, different types of fruits and berries, hay, logs, wood, mushrooms, things like that. These type of esters are really responsible for many, many, many of the aromas of many compounds. So again, how would we draw hexyl pentanoate? Hexyl is the group coming off the O. So this is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh, 6 for hexyl. 6, hexyl group. And then pentanoate would be 5 carbons. So we've got 1, 2, 3, 4, 5. Double check. 1, 2, 3, 4, 5. There we go. So this would be our hexyl pentanoate. So again, you'll see the type of variety of these that you can actually synthesize and actually find the different smells of. Isoamyl acetate is one of my favorites. That's the banana. It's isoamyl is a specific type of naming system, but it's an ethanoate or an acetate, and it is a 5-member, but it's isolated, so it's an isoamyl group. A little bit different than a straight chain. Let's double check our work. So again, 1 propanol right here plus ethanoic or acetic acid. This group is going to be attached to here, and we're going to get propyl ethanoate there, or propyl acetate. You'll also see it's acetate again. It's hard to get away from the acetic acid. And then they use acetate instead. But this is the proper way to be naming those. Plus water as a byproduct. Okay, moving on. So instead of an OH group or an R group or an H, what if we have an amine there? These are referred to as amides. Or amides, I guess, although I don't hear that said very often. Amide is how they're known. So very similarly, what if we take an amine and react it with an acid? It's another condensation reaction. Notice we'll get these coming together to form water. And this is how we're going to form that. So that group will replace that. So we've got an amide on the right-hand side. How do we name these? Well, the suffix is going to be amide, essentially. So instead of, for example, propanoic, we'll change that to propanamide. Propanamide. Same thing here. If we take, it's very similar to naming our esters. So if we take ethanoic acid and add methylamine, so this is an amine but with a methyl group, we're going to get methyl ethanamide. So it tells you what's coming off of the N and where this ethanoic acid came from. So in this case, it came from the ethanoic acid. So methyl to the right came here, ethanamide from the left there. Again, this will take some practice. So again, you're clearly just beginning to learn these naming rules, but we've gone through a lot of these now. So let's go ahead and review. Organic halides. This is where we have some sort of alkyl chain and chlorine, bromine, iodine, for example. This would be chloromethane. Alcohols, we use the OL. So ethyl alcohol is the old way, or we would call this ethanol. That's the better way, but you'll still see this used. Ethers, if we see two different groups in an ether, well, we just kind of name what's on there. This becomes methoxymethane. If this is a longer chain, it would be methoxy, whatever this is. Maybe it's propane, methoxybutane, etc. Aldehydes, we use the al to give this instead of ethanol, like this alcohol, it's ethanal. Same thing for ketones. Instead of using, again, this is prop. Instead of using anal, we're going to use propanone or ethanone, or actually, no, propanone is the smallest one. What am I saying? Then we looked at organic acids. These are the carboxylic acid groups. We use the oic suffix there. Esters, we use the O8 suffix. Amines, we just call amine. In amides, we use the whatever's coming off the N, in this case a methyl. And then where did this come from? Ethanoic acid gets changed to ethanamide. So quite a bit. So you guys will have to be responsible for classifying, identifying, drawing, and naming all of these types of structures for this section. So to end this discussion, I wanted to bring this, I think I remember showing this in Gen Chem once, but what you have here are the ingredients for a banana. This kind of gets to the point that people are afraid of the term chemicals and they want to think all natural. Well, everything are chemicals. So all the flavorings that we have that we find in candy, they might be synthetically engineered, but most of them we discovered by analyzing what's inside a banana. So what's inside a banana? Well, we've got mostly water, sugars, glucose, fructose, sucrose, maltose. What else? We have a whole bunch of amino acids. We have fatty acids. These are carboxylic acids. And we also have colors, kilo orange E101, as in riboflavin. And check out some of these flavors. Ethanoate. Oh, okay. We've got some esters in here. 2-methyl-butyl ethanoate. We've got 2-methyl-propan-1-ol, some alcohols. Lots of esters. We have a 3-methyl-butanal. That's going to be a, let's try to draw that. What's 3-methyl-butanal? This is an aldehyde. But tells us it's 4-chain long. Aldehyde has to end there. This is the 1 position. So 1 carbon, 2, 3, 4. And then at the 3, we have a methyl group. So 1, 2, 3. So we got some of that in there. That's one of our flavorings, our chemical flavorings in an all-natural banana. Ethyl hexanoate, another ester. Pentyl acetate, another ester. Notice they're using the not ethanoate, they're using acetate there. So it's just kind of interesting to see all these things and think, whoa, this looks, if you were just to show this to someone who didn't understand chemical terminology or just didn't understand science, they would think, wow, this is a processed food. Like, look at all these processed sounding flavors and just some weird stuff. No, these are all absolutely natural occurring compounds with systematic names. They're not scary compounds, they're just systematically named. So I thought that was pretty interesting. The classic all natural banana. So that is the end of this section. And really the whole 21.5 is just introducing aldehydes, ketones, carboxylic acids that we can get by actually oxidizing alcohols to get there. And then we looked at esters, which are formed by condensation of carboxylic acids and alcohols. And then amides are condensation of carboxylic acids with amines. And all the naming that goes with it. So again, lots of practice will get you ready for the exam. And I'll see you guys in the last section about polymers very soon.